Hi, today I'm going to show you how to implement TOTP in C. TOTP stands for time-based one-time passwords, and it is a standard of two-factor authentication popularized by the apps such as Google Authenticator and a multitude of different apps that you can download on Play Store and App Store. And if you're anything like me, you may have wondered how they work and what's actually hidden behind all these fancy codes. My name is Karol Moros. It is Friday, February the 28th, 2025, and you are watching Make Programming Fun Again. So I had a few times when I wanted to switch to using a dumb phone instead of using a smartphone. And for a long period of time, the problem I've encountered was always that I was using several services that relied on TOTP. For example, if I wanted to sign into GitHub or GitLab, I couldn't do it without a smartphone. Now, I later found out that it's actually not so difficult. You do not really need a smartphone to generate these codes. And everything is just a hash function with some extra steps. And in this video, I'm going to show you how exactly this works and how you can implement this in C. So if you are working on macOS, you're going to have to install OpenSSL, and you're going to have to set up some compiler flags and linker flags so that your client compiler can find the header files and the libraries. And I'm not going to go into too deep into this subject, but I will leave a link to the repository in the description. And if you want to follow this video on a macOS machine, you can use this code. Anyway, the first step in a TOTP workflow usually starts with the website showing you a QR code and telling you to scan it with your phone. And these days, you don't even really need an app like Google Authenticator. iOS has support for these codes iOS supports these codes in the camera app, and you can even add these TOTP codes to the iCloud passwords. And also there are apps like KeePass or 1Password that can also do this for you. So the way this works is this QR code encodes this URL, and this URL is defined in there is a website on GitHub that describes how this works. So basically, this is a URL with a schema of OTP auth, and it contains this part defines that we are doing TOTP and not HOTP. More about it later. And this part shows your email, but it is really optional because the most important part of this whole URL is this secret value. And this secret value is encoded in base 32. And this is exactly the reason why I showed you how to implement base 32 decoding and encoding functions in the previous two videos. And this sample URL uses all of the query string parameters defined in this specification. It contains a secret. It is 32 bytes. I think it is 32 base 32 letters. So the corresponding secret is 20 bytes long. It contains an optional issuer field. It defines the algorithm as SHA-1, but actually it is HMAC SHA-1, and also this is the default value. It defines the code to use 6 digits, but this is also the default. It defines the period for which each code is valid to be 30 seconds. And it also contains this optional email field. And anyway, if we omitted everything else and just used this secret, it would probably just work just fine. Maybe with a bit worse user experience, but it would still work fine nevertheless. So the first thing we need to do in order to generate a TOTP is we're going to need to decode this secret. So I'm going to start by opening this, opening the code editor. Let's see what I have in this folder. What do I have in main? Okay, this is code from previous videos, and I'm going to use it so that we can have some basis to go on. Basically, this just calls base32 encode and decode in order to let us encode and decode base32 encoded binaries. And I think I could just remove everything other than... Okay, I'll just remove everything here, and we will just start from scratch. Anyway, in base32h, we have defined two functions. One of them is called base32 decode, and the other one is called base32 encode. And in this video, we only really care about base32 decode because it is the one we're going to use to decode this string of base32 encoded data into a binary. So I'm going to, like in a real world situation, we will probably be storing this these keys somewhere, I don't know, in a database probably. And I'm going to define a uint8t vector called key, and this is going to be 20 bytes because we know that the hard-coded secret is exactly 20 bytes long. And I'm going to call base32 decode from the secret to the key, and it is 20 bytes long. What does it say? Okay, uint8. The parameter of type char20. Why is it so? Haven't we used base32? What are we using in base32 decode actually? Okay, so for some reason we are decoding into a char and not an unsigned char. I think this is a mistake. We are going to deal with unsigned chars because this is binary data. So I will also need to update the header files, and this is going to be uint8t, like so. So in main, okay, we have this secret key, and we could try to print it out to see if we have correctly decoded it. I have in this slide I'm showing the base32 encoded secret on the top, and below is the corresponding binary form. So I'm just going to quickly print it out in hex format. So this is going to be 0 to x, key I, and we put a new line at the end. Excuse me. Let's see if we can compile it. No, not here. Make main. Undefined reference to base32 decode. What do you have in makefile? Okay, make. I'm going to define a new target in here. I'm going to call it TOTP. and it's going to be to depend on main.c and base32.c, and yeah, the rest is going to be the same, I think. What do you mean undefined reference to base32 code? Okay, make TOTP. Okay, so now if we run this, what do you mean? All base32. No, I want it to be. Was it this one? Okay. So now I have to modify this makefile so that it could show me so that it could output the code to a file named TOTP. And as you can see, this worked. Also, pardon me, I have to check something. Yes, so where was I? TOTP. I have modified the makefile so we could output the the result of main.c and base32.c into a file named the same as the target. And we quickly verify that the base32 encoded key could be successfully decoded as binary by like superficially looking at all the decoded hex codes. It looks like this is working just fine. And I think we may want to define a function to help us debug. What just happened? Sorry, sorry for that. I realized I did not silence all the notifications, and I realized and somebody started texting me. This was confusing. Anyway, I'm going to define a quick subroutine to debug binaries. And this is going to take a uint8 pointer. And it's going to take a length, size t length, and like so. We are going to output this from the buffer, and we put a new line at the end, and I think we could also add a space for prettier output, and debug binary key, and the length is 20. Make TOTP. Okay, TOTP. It prints the beautiful key. Great. And so this was the first step. The second step is you're going to need to get a Unix timestamp. And if you're not familiar with the term Unix timestamp, this is basically, it is a so-called epoch timestamp. It is a time format which relies on a starting date. So the starting date for a Unix time is 1970 0101 000000 UTC. So it's midnight, January the 1st, 1970 at UTC. And I have tested this code on macOS and Linux, and it compiles fine. So I'm going to basically implement this function in here. Static time t Unix epoch, and yep, struct time spec tp clock get time Also, this has to be time.h, clock real time pointer to TP, and return TP tvsec. Okay, great. So this is going to be return the second part. And now that we have the key, we can calculate the step, and the step is calculated like so. We take the I'm going to put it in a 64-bit I'm going to put it in a 64-bit integer, and this is going to be the step or time step, and this equals to Unix epoch divided by 30, and then I'm going to print it out so we can test if it works. Yes, printf ldn time step, like so. I'm going to compile it and run it, and I'm not entirely sure if this is the correct value. We will see in a moment. So the next thing we have to do is we're going to have to take this time step thing, and so time step is currently a 64-bit integer, but we need to encode it into a binary so that we can pass it to the hash function. So I'm going to define another helper function, and it's going to be void, and it's going to take encode. I'm going to call it encode time step. It's going to take the pointer to, no, it's not the pointer. It's going to take the time step variable, and it's going to take a pointer to a binary vector called destination, and for int equals I equals 0, I is less than 8, I plus plus, destination at index of I equals step is going to be moved right by 7 minus I times 8 and masked with 1 byte, like so. So this looks pretty cryptic, but it basically just means that we start from the first byte, which is at index 0. We take this whole value. We move it a number of bytes to the right. So for example, if we want to take the first byte, this is going to be at index 0, and we want to move it 7 bytes to the right, which means that index is this is going to be 0. We subtract it from 7, which means we're moving it 56 bits to the right, and then we mask it with a single byte, like 0xFF, which will convert it to a single 28-bit value, and then we can put it in the destination binary. So I'm going to call this encode time step function with the time step, and the destination is going to be I'm going to call it I'm just going to call it T, because this is I think this was one of the names that was used in the RFC, and the destination is going to be T, and then we can call debug binary with T and length of 8. Now compile it and run it. Okay, why does it run so many times? Okay, this is because we didn't include this bound like this. Okay, so this is the step in decimal, and this is the step encoded as a 64-bit big endian binary. And if we check with our reference value, yes, sorry for that. Where was I? We have this reference value of that I'm going. We have this reference value that we are using in this presentation, and if we run the program again, we get the same reference bytes. It ends with 5F, 63 5F, 63 5F, and then the next step is we're going to have to calculate an HMAC SHA-1 signature or digest of this time step value. And in order to do that, we are going to need to use OpenSSL. And if I remember correctly, it was EVPH and CryptoH. And we're going to define a buffer for this digest thing. It's going to be 20 bytes long. And I'm going to leave both debugs for now. And we call the function HMAC okay, I think I need to define a clang the file in here. Did I have a clang file in here? Okay, it's compile flags. Add -i. Where is this OpenSSL? EVPH. Do I have man HMAC? Okay, it's OpenSSL HMAC H. Okay, so it's like so. So I don't need to add any compile flags for now. And now this is going to take EVP SHA-1 and then so the first argument to HMAC is EVP SHA-1. The second one is the key. The third one is the length of the key. Then the pointer to the destination. The length of the what was it? Data length. Okay. So this is going to be, the second is going to be the timestamp value, then the destination, and the destination is going to be okay. Yeah, this is going to be another variable, size t length, and wait, what does it want? Digest EVP MD key length, data length, pointer, and this is going to be int unsigned int length. Okay, so it should compile, it should calculate the HMAC SHA-1 value, and let's debug it. And like so. And if I try to compile it now, we're going to get an undefined reference to EVP SHA-1 because we need to add some compiler flags. So I'm going to add some compiler flags in here. Oh, we don't need compiler flags, we need LD flags. And that's going to be L crypto LSSL. I think. And I'm going to pass this here and see if this works. Okay, so I added these lcrypto and lSSL flags. If you're going to work on macOS, you're going to need many more flags, but this should be enough on Linux. So now if we look at the reference values, the timestamp ends with 68 and the signature computed for this timestamp ends with D477B. So it means we are getting a correct signature. So far so good. And now what we're going to do is we take the last 4 bits of a signature, and in the case, the timestamp changed, so the signature ends with 56C8 now. We take the last byte, which is C8. We mask it with 0xf, and we get the last 4 bits, and this is going to be 8. And then we take the 4 bytes starting from index from the index indicated by the last 4 bits of the digest. So in this situation, we can say int offset equals digest at 19 mask with 0xf, and then you int 32t binary, and we're going to take these 4 bytes and we're going to treat them like a 32-bit unsigned integer, and we discard the sign. So it more or less looks like this. I'm not going to copy this this part because I'm not sure. I'm just going to type it out for now. So yeah, that's basically digest at offset plus 0 and mask with 0x7f and move 24 bits to the left so that it stays in the first byte, and the remaining part of the expression is pretty much similar. Digest at offset plus 1. We don't have to mask it anymore because we're going to use all the bytes, and then digest offset plus 2, move 8 bits to the left, and then digest offset plus 3, like so. And then the OTP is going to equal binary modulo 1 million, and we can print it out with %06D OTP. So now I'm going to compile it again. I'm going to run it, and now we are getting a 6-digit TOTP code, and our reference implementation returns the same code, like so. And just to be on the safe side, let's see if this also works with a real quote-unquote real authentication library, and it also returns the same code as the one shown in the screen. Great. So this basically means that in less than half an hour we implemented things that some people sell as a subscription. That's kind of devastating. But yes, TOTP is very simple. And if you like my explanation with a lot of interruptions, please like and subscribe. And if you did not enjoy this explanation, please let me know why, so I can get some traffic from your comments. And I hope you learned something useful, and I will see you in the next video. Bye.